John Dalton's resurrection of the idea of atoms incited a flurry of activity amongst chemists as they went about studying the different kinds of atoms they could discover and comparing their weights and their chemical properties. From this emerged a debate on how to organize all of these so-called elements. Those who thought that the chemical properties were the most relevant on one side of the argument, and those that thought that size was the most important on the other side. This debate was largely resolved by this Russian chemist named Dmitry Mendeleev, who realized that these two ideas were not mutually exclusive. So he compiled a master list of all of the elements that other people had studied, and he started arranging them both in terms of increasing size, while also keeping track of their special chemical properties. This table eventually came to look more like this: the periodic table of the elements. You'll notice that the old word element from Aristotle resurfaced at this time to denote a type of atom. And in the periodic table of the elements, each element gets its own name, its own symbol, and its own number. Take a couple examples that we'll be studying a lot this year. For example, carbon, which is right here, has an atomic number of 6, which you can see in the lower left-hand corner, and a symbol of C. Hydrogen, an atomic number of 1 and a symbol of H. Oxygen, 8 and O. N stands for nitrogen, which has an atomic number of 7. P for phosphorus with an atomic number of 15. And S for sulfur with an atomic number of 16. And these are the 6 most common elements in organisms, as we'll learn later. These increasing atomic numbers, so hydrogen 1, and then helium 2, and then lithium 3, and beryllium 4, those denote the increasing size of each atom. And so you can see as the atoms get bigger and bigger, they get more and more rows inside the table. And each row in the table is called a period. You'll learn a lot more about these periods in chemistry class, but for our purposes, the thing to notice is that as you go from period to period to period, 1, 2, 3, 4, 5, 6, and 7, the atoms get larger and larger. So, elements arranged by size. Now, the elements are also arranged by chemical properties as shown by their group, also sometimes called family. The elements in each family often share chemical characteristics. So, for example, all of the alkali metals, which are here in group 1, have a tendency to react with water very violently. So, there was a chemistry student at my college who wanted to make a prank in the chemistry department, and he decided to take a huge chunk of potassium, represented by K, and toss it in one of the toilets, which caused the entire toilet to explode. And this chemistry student could have chosen any of the alkali metals, any of the elements inside this family or group, because they all react with water very violently in order to carry out his prank. Contrast that with the noble gases that are way over here on the right, in group 18. They don't react with anything. They're never participating in chemical reactions. They're known as inert. So you can have these two extremes, and they're both represented in different groups. So the periodic table of the elements gets that increasing size idea from period to period, but also represents those unique chemical properties from group to group. So brilliant chart if I've ever seen one. But what's the physical difference between each of these elements? What are the different atoms made of? The answer to these questions required many more experiments. There's a trend in science that whenever you want to understand how something works normally, look at it when it's not working normally. Early ventures into the realms of atomic structure follow this rule, as Becquerel and the Curies shown in these pictures here studied some very abnormal versions of elements called radioactive isotopes. An isotope is a version of an element with an abnormal number of neutrons in its nucleus. Now, Becquerel and the Curies had no clue what a neutron was or what a nucleus was. However, they did stumble across the special properties of radioactive isotopes, Becquerel entirely by coincidence. So he took some radioactive uranium salts, and he was going to run an experiment on them one day, but then he ran out of time, and so he took those salts, he wrapped them up in some foil, and he tossed them inside a drawer. By serendipity, he tossed them on top of some photography paper, which you can see right here, and when he pulled the photography paper out, even having never exposed it to light, he noticed that the photography paper developed on its own, or seemingly on its own. It developed in the exact shape of the uranium salts that he had left on top of the paper. Hereby, he discovered that some substances, such as uranium salts, give off radioactivity, which can be detected by photography paper as it was by accident in his case. Pierre and Marie Curie, especially Marie, continued to study uranium salts and other kinds of radioactive isotopes on their own. For her research, Marie Curie became one of the most famous women in science ever. Compare that with poor Madame Lavoisier, who was a lot smarter than her husband, and who did most of his research but had to publish under his name. Marie Curie, on the other hand, was actually made the first woman professor of Université La Sorbonne in Paris. She also received multiple Nobel Prizes in different kinds of science, so a brilliant woman who luckily got some recognition for her brilliance. This diagram is a modern understanding of what the Curies were studying. So they would take this large uranium nucleus, which was a radioactive isotope, which was so large and unstable that from time to time there would be a decay event, meaning that the nucleus would spontaneously give off what was called an alpha particle. We now know that alpha particles contain 2 protons and 2 neutrons, and so it overall has a positive charge. The Curies didn't know this, they just knew that overall the particle was positively charged. Nonetheless, this was very surprising because they would get an overall neutral atom, and coming out of this atom would be something with a charge on it. So that's weird. That suggested to them that perhaps there were parts inside of atoms, and those parts must have had charges. A further mystery was that after this decay event occurred, the resulting atom down here actually changed elements. Where it was once uranium, it became thorium. This told them that the number of protons and neutrons, or the number of particles that were hidden somewhere in these atoms, had something to do with the identity and the properties of those atoms. But they did not have such a sophisticated picture in their head. That required even more experiments just to figure out what are these charged particles inside an atom. In 1897, Thomson discovered one of these so-called subatomic particles, now known as the electron. He demonstrated its existence using one of these cathode ray tubes, which you can see in the picture here, which I'm going to diagram to the right. A cathode ray tube is evacuated. That means the inside of it is a vacuum, so there's no air. And he would run wires to either end, one of which would be positively charged and the other of which would be negatively charged. Now, charged metals give off electricity, and he could get the electricity to go shooting across the middle of his cathode ray tube from one end to the other. Now, this beam, or constant spark of electricity that was running from one node to the next, had some special properties which he discovered when he started to play with some magnets. So, for example, if you took a magnet and he put it in this orientation, with the positive end pointing towards the beam, then the beam had a very interesting behavior. It would start to deflect like this. Ooh, it would start coming down this way before it would go shooting back up to the node. In contrast, if you put the negative end of the magnet towards the beam would have the opposite behavior. It would deflect to the other end of the tube. This really puzzled Thomson, and he was worried that some confounding variable had slipped into his experiment, so he went back in and built a whole bunch more cathode ray tubes, and each time he would use a different metal for the node, but always the same thing. The particles would always deflect away from the negative end of a magnet towards the positive end of a magnet, and they would always deflect the exact same amount. Now, in electromagnetism, opposite charges attract and like charges repel. This left J.J. Thomson with only one conclusion. The beam must have a negative charge, because only a negative charge would go zooming towards this positively charged end of a magnet and would go zooming away from the negatively charged of a magnet. And that in turn meant that, since any metal he used for his cathode ray tube would always deflect the same amount, that means that any metal, and probably any substance, period, had to have a negatively charged particle inside of it. He called this particle the electron, negatively charged. And then he sat back to imagine what the atom must look like. His idea was that the atom might look something like plum pudding. So there would be an atom like this plum pudding right here, and each of the plums inside the plum pudding would represent an electron, these negatively charged particles. Now, Thomson knew as much as the next person that most substances don't have an overall charge. So if I held a magnet up to your face, it wouldn't stick to your nose. So however much negative charge there is in an object, there has to be an equal amount of positive charge. Thomson imagined this as a sea of small positive charges that made up the actual pudding, in which the electrons, the big negative charges, were floating. Of course, this plum pudding model was mostly conjecture. The only thing that J.J. Thomson had proved was that electrons exist. Where are the positive charges, though? Other scientists had to go hunting for them. And that brings us to Ernest Rutherford's gold foil experiment, perhaps the most important experiment ever done to develop our modern understanding of the structure of the atom. Rutherford wanted to test J.J. Thomson's hypothesis that atoms had this sea of light positive charge. If there was indeed light positive charge, then a heavy enough object could go shooting through that cloud and get through to the other side relatively easily. The object that he chose was the alpha particle that the Curies had studied, and so he took some uranium salts, just like what the Curies had used, and he put them inside of a lead shield. So that made it so that the radioactivity would only come out of one single little hole, like you can see right here. Almost like he was setting up a cannon, and out come the cannonballs. They come zooming in this direction. Right in the line of fire, he put some gold foil. He used gold because it's one of the most malleable metals, and he could hammer it very, very, very thin. His thought was, if I get this foil thin enough, and if J.J. Thomson's hypothesis is correct, then this beam of alpha particles should be able to pass right through the gold foil without bumping into anything. An alpha particle, though he didn't know exactly what it was, he knew was massive and positive. And if there was just a sea of positive charge inside this gold foil, then these particles should be able to zip right through that gold foil right to the other side to be detected here by some photography paper. And indeed, that's what he found 99% of the time. However, the exceptional 1% changed the course of science. A few of the alpha particles didn't go straight through. Instead, they ricocheted off of something large and massive inside the foil and ended up bouncing back and going in different directions. When Rutherford got this result, he could not believe his eyes. Here's what he wrote about it in his journal. It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper, and it came back and hit you. On consideration, I realized that this scattering backwards must be the result of a single collision, and when I made calculations, I saw that it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute nucleus. It was then that I had the idea of an atom with a minute, massive center carrying a charge. That's what he wrote in 1911. So basically, the fact that these particles bounced off told him somewhere in this gold foil there has to be very concentrated, very massive amounts of positive charge. So if I zoomed way in, as the alpha particle came in, most of the time it must go passing through, because after all, most of the beam went right through to the other side. But every so often, that alpha particle would strike something that was large and, larger than it was, and also had to be positively charged, because what would happen when the alpha particle approached it? They would repel and it would go zooming off in another direction. So in this way, Ernest Rutherford gave the first suggestion of the nucleus at the center of an atom that contained positive charges, such as protons. Many experiments later, you get to this modern Bohr model of the atom, which we will use in this class, in which the nucleus contains most of the mass of the atom, present in protons and neutrons, and the electrons, small particles, go zooming around the outside of the atom. And the vast majority of the atom is actually empty space. It is an arresting notion to think that every object in the universe is made of atoms, and that atoms are mostly empty. But indeed, that is what the gold foil experiment showed. The fact that most of the particles would go right through says, all right, well, if particles can go right through it, then there's nothing there at all, which means that atoms are mostly empty. And when I say mostly empty, I mean it. Picture for a moment Gillette Stadium. The nucleus of the atom would be the ball sitting in the middle of the field. The electrons would be the size of a fly flying around the outside of the stadium. And the rest of the stadium, the rest of the atom, is empty space. Aristotle would never have dreamed of such a model for an atom, and yet science and observation and careful experimentation eventually led us to this very surprising understanding.